Hello drives embed friends. Welcome to this introduction. Most available electric drives provide the torque Tm, which responds to the command Tref, with a time lag, ranging several tens to several hundreds of microseconds. The motor torque is determined by the current circulating in its windings. Consequently, the torque response time depends upon the current control loop bandwidth, and is therefore limited. Hence, the desired transfer function W of S equals to a constant can hardly be achieved. On the other hand, the desired speed loop response is measured in tens of milliseconds. In most cases, delays introduced by practicable torque actuators are negligible compared with the dynamics of the mechanical subsystem and the desired response time of the speed loop. In such cases, the speed loop analysis and tuning can be performed under the assumption that the torque actuator has a static gain and no associated dynamics or delays. The speed feedback omega FB is obtained at the output of the block Wm of S. The feedback signal omega FB is not an exact copy of the actual speed omega, due to a limited resolution of some shaft sensors, owing to the need to filter out the noise and high-frequency content, and due to specific techniques of speed signal acquisition and signal reconstruction. The transfer function Wm of S describes the signal processing within the shaft sensor and the associated circuits. If we consider a brushed TAC generator with an RC low-pass network, so this will be the transfer function. In cases when electromagnetic resolvers are used, the function Wm of S is more complex. In the design and tuning of speed controllers, the transfer function Wm of S must be taken into consideration. In cases when time constants involved in feedback filtering and processing are found to be considerably smaller compared with the desired speed response times, the function Wm of S can be neglected and considered equal to 1 omega FB. Specifically, the TACHO filtering RC network, with tau equals 100 microseconds, can be ignored in designing a speed controller with a desired rise time of 10 milliseconds. We now use this speed control system in the preliminary analysis of speed controllers. It has an idealized speed measurement system and a torque actuator that provides a driving torque Tm equal to the reference Tref. The system makes use of a separately excited DC motor that drives an inertial load. The excitation current Ip and motor field Φp are assumed to be constant. Therefore, the torque is in direct proportion to the armature current Ia. For the given driving torque Tm, this is the armature current Ia, where Km is the motor torque constant. For this reason, the torque reference Tref, derived from the speed controller Wsc of S, becomes the armature current reference. For the simplicity of this introductory considerations, the power amplifier supplying the armature current is reduced to an idealized, controllable current source. In practice, the DC drive power amplifiers operate on the basis of commutating the switching power transistors, or thyristors, and they are associated with an analog or digital current controller. The amplifier supplies the armature voltage to the motor. The armature current changes according to this equation. The current controller actuates the power switches in order to obtain the voltage UAB, that compensates the back EMF, and suppresses the error delta I. The current controller produces the voltage reference, by multiplying the error by the proportional and integral gains. With sufficiently high loop gains, the error delta I has negligible values. In such cases, the impact of the electromotive force EA on the armature current can be neglected. Further considerations assume an ideal current controller. Most modern speed controllers are implemented digitally. They are located in the program memory of microcontrollers and digital signal processors for motion control tasks. In other words, their control actions take place at discrete, equidistant moments, synchronized by the interrupt events of a microcontroller or DSP. The analysis, synthesis and tuning of these discrete time-velocity controllers involve the representation in the Z-domain of the relevant signals and transfer functions by using Z-transformation. Prior to digital speed controllers, the speed control functions WSC of S were historically implemented in a continuous domain, mainly by means of analog electronic circuits, comprising operational amplifiers, resistors and capacitors. Ancestors to digital controllers, the continuous domain speed controllers, are frequently referred to as analog. The analysis of analog speed controllers includes the representation of S-domain signals and functions by using Laplace transformation. In the next videos, we start to analyze the speed controller design concepts. An insight is given into the closed-loop bandwidth and the parameter setting. Discussing the impact of various disturbances on the speed controller structure, the feed-forward control and internal model principle are explained.